This is the outline. First, I will briefly introduce generalized Parton distributions and the way to access it, deeply virtual meson production. Then I'll present a neutral pion electroproduction analysis that was done in Hall A experiments in Jefferson Lab. Then I will show you a new neutral particle spectrometer being developed for the upcoming Hall C experiment in Jefferson Lab. And finally, but shortly, I will discuss this new calorimeter material, which is a candidate of the calorimeter for a future Electron-Ion Collider. So protons and neutrons, I think you all know, are the basic building blocks of the matters of the visible universe, and they form nucleus or atom, and atoms form everything that is around us. We call proton and neutron nucleons. So nucleons interact by strong force, and they are described by the QCD. The degrees of freedom of the QCD are quarks and gluons. However, the quarks and gluons get confined in the nucleon in a large scale due to increasing coupling constant in QCD. Therefore, there exists some challenges understanding the QCD quantitatively. And one of the ways to study the QCD in this non-perturbative region is lattice QCD, which approaches that region with numerical Monte Carlo simulation. Another way of the approach is studying the nucleon structure. So by experimentally studying the structure of the nucleon, we can find clues on how this non-perturbative region of the QCD works. And here are some examples of the parameterization of the nucleon structure. So in the middle, bottom of, on the bottom and on the middle, it's a form factor. This is the form factor, which is accessible by elastic scattering, gives us spatial distribution of the parton inside the nucleon. And on the left, the parton distribution functions, which is accessible by deep inelastic scattering, gives us longitudinal momentum distribution of the partons inside the nucleon. And these objects has given us many information for decades, but there are disadvantages. Form factor has no momentum information, and parton distribution has no spatial distribution of the partons inside the nucleon. And on the right, this relatively new object called Generalized Parton Distributions, GPD, correlate this spatial, transverse spatial and longitudinal momentum information of the partons in them. So we can have more richer information of the partons. And we can define even more generalized objects than GPDs, and it is called Wegener distribution. Wegener distribution depends on three-dimensional momentum and two-dimensional transverse position of the partons of the nucleon. And if we integrate this Wegener distribution over the transverse moments of the parton, we get the GPDs. And if we integrate the GPDs over the transverse position of the parton, we get the parton distribution. And if we integrate over longitudinal momentum, we get the form factors. And we can access this generalized parton distribution GPDs via exclusive reaction, which means we know all the form momentum of the initial and final particles in the process. And one of the simple exclusive reaction is deeply virtual meson production, DVMP. So this is meson electroproduction in Birken limit, and Birken limit is defined as described in the middle here. The initial photon, usually emitted by lepton, interacts with one of the partons inside the nucleon, and in the final state, a meson is produced, and parton with this changed momentum gets reabsorbed to the nucleon. And at sufficiently high Q square, Birken limit, the DVMP amplitude can be factorized into two parts, hard part and the soft part. And we can draw the DVMP diagram as shown here, and we call this handbag diagram, because it looks like handbag to someone. So you can see there is only one parton associated in the process, and we call this leading twist. And at higher twist, there will be additional parton coupled to the hard part where the parton and photon interacts, to the soft part where the rest of the nucleon lies. So at leading twist, or shall we say handbag diagram, this hard part where the parton and photon interacts is perturbatively calculable, whereas the lower part where the nucleon structure we want to extract is embedded gets parameterized by this universal quantity, GPDs. And there are 4 chiral even GPDs, and they keep the helicity of the partons unchanged. There are also 4 chiral odd GPDs, which flips the helicity of the parton, but they are highly suppressed due to helicity conservation. And the GPDs depend on 3 variables: momentum fraction x, and xi describing the skewness, and t, the square momentum transfer between the initial and final proton. So by measuring different types of meson, a flavor separation of the GPDs are possible, and we can also test the universality of the GPDs. When this handbag diagram dominates, the sigma L dominates over sigma T, and sigma LT corresponds to cross-section of the meson electroproduction, responding to the polarization state of the virtual photon, L for longitudinal and T for transversely polarized. Well, and through sigma L, chiral even GPDs are accessible. However, this sigma L dominance over sigma T is not experimentally observed yet, which is the case for handbag diagram dominance. Dominating. And there are some models describing this sigma T dominance over sigma L using a chiral odd GPDs. Yes. I think I should mention that the easiest exclusive reaction we can think of is actually deeply virtual Compton scattering. Instead of meson production in the meson produced in the final states, for the deeply virtual Compton scattering, there's a real photon in the final state. And here are some examples of the properties of the chiral even GPDs at leading twist. In the parton level, shown here with the red, the GPDs without the tilde overhead corresponds to the averages over the parton helicity, and with the tilde represents the difference of the parton helicity. And in the nucleon level, GPDH conserves the nucleon helicity, while GPDE flip it. Since the GPDs are the generalization of the form factor and parton distribution functions, they should reduce to the usual form factor and parton distribution in certain limits. For example, if you integrate GPDH over X, you get the Pauli form factor. And if you take it to the 4 limit, you get the parton distribution functions. And another feature of the GPDs is that if you get the second moment of the sum of GPDH and E, you get the total angular momentum contribution of the quark to the nucleon spin. The chiral odd GPDs have got less theoretical and experimental attention compared to the chiral even GPDs. As you obtain the transverse charge radius of the form factors by performing Fourier transformation, we can also obtain longitudinal momentum fraction x dependent radius of the quark density in the transverse plane of the proton. And here on the left is this 3-dimensional representation of the proton transverse charge radius, where the direction of the cone shape indicates the momentum fraction x, and the transverse direction indicates the proton's transverse charge radius. And this shows that the fast-moving quarks are mostly concentrated at the center, and slow-moving quarks and C quarks are around the edge of the nucleon. So these are only few features of the GPDs, and it needs more experimental data to actually extract them. The cross-section for the meson electroproduction, in my case, neutral pion, can be decomposed into the cross-sections, each corresponding to the polarization of the virtual photon. And here sigma TL and sigma TT corresponds to the interference of the polarization, interference term of the polarization. And in order to access the GPDs, we need to separate each of these cross sections. And since they have different phi modulation and kinematic coefficient, we can separate them. The phi here is defined by the angle between the leptonic plane and the hadronic plane. And the leptonic plane is defined by the direction of the scattering electron and the virtual photon. And for the leptonic hadronic plane, by the recoiling proton and the pi0 direction. And by using only this phi dependence, we cannot separate the sigma T and sigma L in the same kinematics. They can be separated using different beam energies, but I'll talk about that later. And these kind of reactions have small cross-section, so high luminosity of the experiment is required to measure them. And one of the best facility in the world that has those capabilities is Jefferson Lab. Sorry. The Jefferson Lab is in Newport News, Virginia, and it has 12 GeV continuous electron beam and has four experimental hole A, B, C, and D. And they have different setup. Hole A has high momentum resolution. Hole B has large acceptance. Hole C with higher momentum reach, and hole D use 12 GeV photon beam. Yes, I said it's 12 GeV electron beam, but actually in the experiment we use 11 GeV because we create electron accelerate to linear accelerator, and each time it goes through the linear accelerator, it gets 1.1 GeV. So if we go 5 times, we actually get 11 GeV beam. And hole D on the other side gets 12 GeV. And this is the kinematic region that we probed for the whole A DVMP experiment. And this was the first experiment using the upgraded 11 GeV from 6 GeV. And the left plot shows this kinematic region by X Birken and Q square. And the gray area show on the left is the physical limit that we cannot access through 11 GeV beam. And the gray area on the right shows the kinematic, the resonance region that we want to avoid. So we will reach high Q square and we will cover most of the area that 11 GeV can access. So by reaching the high Q square, we will test the dominance of this handback diagram to validate whether the GPD formalism of the DVMP in this kinematics works. And well, this is one of the highest luminosity experiments that exist. So we will have the high precision data in this kinematic region accessible by 11 GeV electron beam.
Hossein, do you mind if I interrupt you? Yeah.
Sorry?
I guess, why do you need to avoid the resonance region? Just to make sure we're following?
So, sorry, then if I emphasize again, GPDs are accessible by exclusive reaction. So exclusive, if you want to measure the GPDs on the proton, in the final states, we want to have the proton intact in the final process. So if we go to resonance region, we will have a bunch of other particles being created. So we will just have hard time analyzing the data.
I see, thank you.
Shall I continue?
Mm-hmm. Yeah.
Yeah, thanks.
And this is the experimental status, apparatus of the hole A experiment. So hole A has 2 giant dipole magnet spectrometer, but we used one of the dipole magnets. So when the electron beam hits the target, which is liquid hydrogen, the scatter electron gets detected by this high resolution spectrometer and detect the scatter electron. And the pion, pi0, which decays to 2 photons, is detected by this electromagnetic calorimeter made of 208 lead fluoride crystals. We don't actually detect the final proton, recoiled proton, but we identify them by using this missing mass technique. So we know all the other 4 momentum of the other particles in the process. So we reconstruct the missed mass and we identify whether this is proton mass or not. So it is kind of very crucial to have high energy resolution on the electromagnetic calorimeter in order to ensure this exclusivity of the reaction. And due to high beam intensity and energy, we, with the calorimeter being this close to the beam pipe and the target, we expect a lot of background on the calorimeter. So in order to reconstruct photon energy from amongst this background and noise on the calorimeter, some sort of energy threshold is needed. So if we give same threshold on all the crystals, there can be underestimation of the photon energy because most of the energy is deposited into one crystal and the rest in the neighboring crystals. So what we do is we actually apply the threshold on the 2x2 clusters. And if the sum of this 2x2 cluster, sum of the energy of these 4 crystals are above a certain threshold, we use them for later for the reconstructing the photon position and energy. And the calorimeter is also designed and placed so that the 2 photons from the pi0 decays are actually separated by at least 1 block of crystal. So the algorithm chooses which energy deposition belongs to which photon, then it enables the distinction between 2 closely distanced pi0 photons. So now we have built the energy and momentum of the photon, and we can now reconstruct the missing mass to identify the photon. And for that process, we also use a Monte Carlo simulation to compensate from these cuts. So let me introduce briefly this this event generator simulation. This is a Geant4 with a realistic experimental apparatus with a pi0 event generator. So pi0 event generator generates pi0 events and calculate the phase space factor of these generated events. And Geant4 handles this particle propagation through the matter. And we have HRS window to detect scattered photon. An electromagnetic calorimeter is fully simulated, but with realistic geometry, but we didn't generate the actual Cherenkov photon for the calorimeter because it is more efficient and faster to smear the energy resolution later when the simulation is done. So this is the one of the examples of the missing mass of the event and the pi0 invariant mass of the event. So pi0, and the red one is from the data and the black one is from the simulation. So pi0 events pi0 invariant mass has rather distinct peak around this mass, but the case of the missing mass distribution, we have a proton mass peak and there's a contamination from the, for example, semi-inclusive DIS events. And of course, the Monte Carlo simulation results do not match with the data because we haven't calibrated and smeared the resolution yet. And this x-axis is the missing mass squared in GeV squared unit. Also, and in the case for invariant mass, this is actually GeV unit, not squared, sorry. The way we calibrate this energy resolution of the calorimeter in the simulation is by matching this missing mass distribution on the proton mass peak side. The gain calibration and the smearing of the energy are performed event by event simultaneously. It multiplies the form momentum of the photon by a random variable following a Gaussian distribution, where mu and sigma are the calibration coefficients and the smearing coefficients, respectively. The coefficients depend on the energy of the photons, and the degradation of the crystal optical transmissions varies for each crystal. The coefficients need to be evaluated for each crystal. Well, that is for an ideal case where there are enough number of events in the experiment. However, it is not the case in real life. So the calorimeter surface is divided into 7 by 7 partially overlapping rectangular areas. So each event is associated to the area where the projection of the pi0 direction lies, and both decay photons are smeared using the same coefficients. So after the calibration and smearing, those 94 areas, we interpolate using those 49 areas to have more smooth coefficients for the smearing process. And this is the after the calibration and smearing. This time, the blue one is from the simulation data and red one is again from the experimental data. Now we see the missing mass distribution and the invariant mass distributions are matching well with the data and the simulation. And by looking the distribution where the experimental data and the simulation data match, I give an event selection cut shown in magenta line to select only the proton event and the pi0 event. And the cyan line on the missing mass distribution represents the data subtracted from the Monte Carlo simulation. And we see that most of the contamination starts around 1.15 GeV squared. With the proton event selection cuts, this mismatch between the data and the simulation is less than 2%. This cut, this proton event cut is actually cut a lot of proton events. So we lose about 40% of the proton, but this Monte Carlo corrects those lost event when we calculate the acceptance. So that's why the data and Monte Carlo should match very well. Now we have the number of events from the experiment. So the number of events detected at the detector, bin R, can be decomposed into multiplication of the integrated luminosity, a cross-section over average cross-section over the bin R, and the acceptance of the bin R. Since we know the number of events and the luminosity from the experiment, and also we calculate the acceptance by Monte Carlo, we get the cross-section. So the basic idea of the cross-section extraction is we minimize the difference between the number of events in the experiment and the Monte Carlo simulation. Due to the radiative effects, the energy resolution of the detector and the energy resolution of the detector, bin migration occurs, and the variables at the target are not always the same when reconstructed at the detector. And this kind of effect is also incorporated into the acceptance calculation. So by doing this chi-square minimization, we obtain a linear equation in the matrix form, and we get the cross-section by solving this linear equation. So before we go to the cross-section results, this is the way I calculate the systematic uncertainties. This is the case for missing mass uppercut, where it's shown here. So by fixing all other event selection cuts and just changing the missing mass uppercut range, then I should see the change of the cross-section results. So above 1.1 GeV squared, the cross-section starts to increase. This is because, unlike data, the Monte Carlo simulation do not have contamination such as semi-inclusive DIS. So that's why the cross-section starts to increase. But below 1.1 GeV, we see rather steady cross-section results. So for the case of here, I give the range for the systematic uncertainty studies. from 0.9 to 1.1 GeV, and I get the maximum value and minimum value of the cross-section and give it as a systematic uncertainties. I didn't go below 0.9 because then I start to cut around the proton mass peak. We lose too much data and it seems a bit ridiculous that study up to the proton mass peak. So this is one of the cross-section, extracted cross-section results. This is the case for sigma T and sigma L unseparated cross-section term. The black dots are the extracted cross-section from the experiment with its statistical uncertainties, and bunch of colored bands are the systematic uncertainties. And this is the combined systematic size of the systematic uncertainty. And I also put a theoretical calculation for the sigma T and sigma L term. You see that by using only the chiral even GPDs, it's the cross-section is expected to, the sigma L term is expected to have very small, whereas the sigma T term is expected to have most of the cross-section. Well, not only for this theoretical calculation, but actually all the GPD models with only the chiral even GPDs can only predict sigma L term, and they all fail to describe this pi0 data up to our kinematic regime. And this model prediction for the sigma T term used the chiral odd GPDs to explain this cross-section results. Maybe it is better to explain with the data, not just comparing with the model calculation. So here now I show you for the same kinematics for sigma TT interference and sigma TL interference. And we see that the sigma TT term and sigma TL term is quite significant, which hints that there is a chiral odd sigma T term has a high contribution to this cross-section. And thankfully, the model prediction also agree well with the sigma TT, but that sigma TL term, however, do not match with the data, which hints there's a larger contribution from the longitudinally polarized photon than the model predicts. And chiral even GPDs might still accessible in this kinematic through neutral pi electron production of the nucleon. And all other kinematics that for this experiment shows similar trends. And now let's see the Q-square scaling. So we saw previously that sigma T term has expected to have higher contribution than we expected. And when we actually see the Q-square scaling, it has a Q-square over minus 6, which is not the case for the sigma TL, which is not the case for the sigma T dominance. So we see that Q-square is still far away from this asymptotic limit. So in order to give a more concrete conclusion, we have to separate this sigma T and sigma L term to directly test this sigma L, whether we are in the sigma L dominance region or sigma T dominance region. And that is the upcoming whole C experiment. And as I have said in the beginning, we need different beam energies to separate each sigma T and sigma L term. And thanks to high momentum range of the spectrometer in whole C, which detects scattered electron, we can perform this Rosenbluth separation. So by fixing all other kinematic variables fixed, we use different beam energies to separate this T and L term. So how do I have 20 minutes left?
Yeah, certainly. Yes.
Okay, I'll go faster. So this is the next section where I talk about the neutral pi particle spectrometer development for the whole upcoming whole C experiment. On the left plot, we see a similar kinematic region accessible by 11 GeV electron beam. And this time, these areas are by hole C experiments. So with these different colors means different beam energies. So at fixed kinematic region, we will change the beam energy to perform this rose and blue separation. And for this experiment, a neutral particle spectrometer, I will show you the background dose rate calculation, energy resolution calculation of this neutral particle spectrometer, and the radiation damage test of this detector. Since we're going to use the highest luminosity of DVMP ever before with the smallest angle as possible, we expect there will be a big amount of backgrounds created on the calorimeter of this neutral particle spectrometer, NPS. So what we have to care about is the radiation damage and the PMT anode current due to the backgrounds. So firstly, we will use a sweeper magnet to reduce the charged particles background going to the calorimeter. Then we'll see. So the calorimeter for this NPS is made of, this time, 1080 lead tungstate crystals. So it will have about 100 times better light yield than the lead fluoride crystal that was used for the hole A experiments. So we will have better energy resolution, and it will have better missing mass resolution. So we will have less trouble in selecting exclusive events. And this is the dose rate calculation results using GR4 with the realistic geometries. There are a lot of plots, but I will explain some of them. The x-axis is the column of this calorimeter. So it represents each column of the calorimeter, and the y-axis is the dose rate in kilorad per hour units. And this black line represents the dose rate without the sweeper magnets, and this red line represents the dose rate with the sweeper magnets. Blue line also represents the same, but with half of the magnetic field strength from red one, from the nominal value. So with this magnetic field strength of 0.3 Tesla meter, it is enough to reduce the charged particle background. For some kinematic settings, it reduces up to an order of magnitude. But if we see the sweeper magnet reduce the dose on the calorimeter. But if we convert this 0.5 kilorad per hour into the anode current at the PMT, it is 1 milliamps. And this is very high currents on the PMT, because PMT manufacturer recommends actually about 1 microamps to 10 microamps. Sometimes if we ask for extreme, they say 100 microamps is maximum. So we don't know when the PMT will start degrading or die completely. This was a problem, but we decided from this, this was the problem occurred from my simulation. And at the end, we decided to decrease the PMT gain by a factor of 2 orders of magnitude, and then amplify the signal after when it goes through the PMT. Since the crystals of the calorimeter will be stacked 30 by 36, and 30 by 36, we need some kind of structure to keep them in a uniform array and also keeping them structurally safe. But if we put too much structure between the crystals, we will lose energy resolution. So by using a simulation, I checked the dependency of the energy resolution on the distance and the material between the crystal. So this left picture here is our earliest prototype design, where the carbon fiber is wrapping each of the crystal, the whole whole side surface of the crystal. And this is the energy resolution simulation results. The x-axis is the beam energy, and the y-axis is the resolution in percent units. And each dot represents the energy resolution. And as anyone can expect, if we reduce the carbon material between the crystals, energy resolutions gets better. These magenta dots are the actual resolution from the other experiment using a very similar design of the calorimeter using about 1,000 lead tungsten crystal. I just put it there to give me some validation. From this simulation results, I can say the carbon structure of the NPS should be less than 1 millimeter. And if we change the carbon material from carbon to air, we get much better energy resolution. So by combining those two energy resolution simulation results, we decided to use carbon fiber frame only at the front of the crystal and the backside of the crystal, and leaving the middle part of the crystal just with the VM2000 reflective sheet and air. And from that, we will achieve the energy resolution better than 1.2% in the energy region of our interest. And for the next section is the irradiation test. The lead tungsten crystal has high energy resolution and is tolerant to the radiation damage, but there still exists some radiation damage to the crystal, and we tested them in LCP, which is now part of the IJC lab. It has 200 terabecquerel cobalt source, and we can vary the distance of the test sample from the source, so we can change the dose rate, and we can simultaneously irradiate 9 crystals at once. And we use transmittance to quantify the radiation change. And transmittance is the radiation flux ratio between the light probe that beam, the light that probe the beam, the light probe the material, and the light that probed the air. And to categorize a good crystal and the bad crystal, we use this delta K value, which is a logarithmic ratio between the transmittance measured before the irradiation and after the irradiation. And on the left plot is delta K example for 2 different crystals. X-axis is the wavelength that the commercial transmittance measuring machine probed, and the y-axis is delta K value in per meter units. And we see that each crystal has different radiation hardness, and we use 1.1 per meter delta K value after 3 kilorad of irradiation to distinguish good crystal and bad crystal for the NPS. And they are sometimes visible, the radiation damage is visible. For good crystal, on the PMT point of view, is transparent, but if it's very bad, the PMT sees nothing. This radiation damage is caused by color centers, which is created by electron traps or point structure defects. The color centers can be relaxed by thermal activation, which means we put the crystals in the oven for 2 hours, or put them in the room temperature for several days or weeks. That is not practical for the experimental environment. So what we use is we tested injection of specific energy. We tested blue lights and infrared light. The PMT is sensitive to the blue light. On the other hand, it is not to the infrared light. So if the infrared light works, there is a possibility of curing the crystal during data taking. So this is the results. One of the results, x-axis is again the wavelength, and the y-axis this time is the transmittance. So Gray is before the before the irradiation, and these dotted lines are the after the irradiation, and the red is after 2 hours of infrared light curing, and the blue is after 2 hours of blue light curing. So we see the blue light works better recovering the transmittance, but we have to remember that the infrared light also works in curing, but with lesser effect. But taking into account that the NPS should be delivered to the Jefferson Lab by the next year, we just decided to use blue light for our curing system of the NPS. And we call this blue light radiation damage recovery using blue light optical bleaching. This is the case for 3 kilorad, which can be converted into 1 hour of high Q square setting and 6 hours of beam time for low X settings. So after 1 hour or 6 hours of beam time, then cure for 2 hours is a bit ridiculous for me. So what we also tested a higher dose, which corresponds to 5 days, 1 day, or several days for other settings. And we tried again for 2 hours of optical bleaching. And it seems the damage recovers most of it when the crystals are good. That can be the conclusion, but we also try to kill the crystal by giving much, much higher dose. So this is about 3 times more than the total expected dose on the crystal during the whole experiment. When the crystals are good crystals, we saw that the radiation damage saturates, which means they don't get damaged below certain level, certain transmittance. But we also saw that the curing effects also decreases. I won't explain the plots because there are a lot of lines, but yes, the result is that the curing effects also decreases. So the good news is, since the radiation damage is saturated, we might not even need the curing for the whole experiment. But we always have to take this into account that it might be possible that not all 1,000 crystals are good as this one on the left. So what we suggest is we apply optical bleaching whenever possible. So whenever the beam stops for some reason, we can apply this method. So finally and shortly, I will discuss the radiation damage, hardness, and the resolution simulation, energy resolution simulation for a glass scintillator. And this is, yes, a glass scintillator for a future Electron-Ion Collider. And this glass scintillator is, of course, made of glass, and this is one of the candidates for the calorimeter of a future Electron-Ion Collider. As shown previously, the lead tungstate crystal has high resolution with high radiation hardness. However, they are expensive. Yeah. And there are several researches to develop a cost-effective materials with decent energy resolution to be used in the EIC calorimeter. Catholic University of America, CUA, is developing this glass scintillator. Although its radiation length is short, its smaller radius is comparable to the lead tungstate crystal. So we can have as compact calorimeter as made of lead tungstate crystal. So that's good news. And it also has better light yield. And the radiation hardness is being measured currently at IJC lab. Not by me, but someone will. So this is one of the radiation hardness tests. This was done exactly the same as the lead tungstate crystal, and the plot you're seeing is very similar. But this time, the blue and black line, both of them represents the radiation, the transmittance measured before the irradiation. This indicates the size of the measurement uncertainty, and the red one is measured after 100 kilorads of irradiation. This kind of uncertainty exists because, as you can see on the left, the sample was so prototype sample, so early sample, that it was very small and had an irregular shape. From here, I cannot have a concrete conclusion, but from this, I can at least say we are in a good start where the radiation hardness, it seems that the material is radiation hard. But to draw a more concrete conclusion, we need a larger and more uniform sample, and they have been recently delivered to IJC lab, and we'll test the radiation hardness of a larger sample. So this is finally my summary and conclusion. The GPDs give richer information of the structure of the nucleon than the form factors and Parton distribution functions. There are 4 chiral even GPDs and 4 chiral odd GPDs, and they're accessible by deeply virtual meson production. And from the whole A, neutral pi electron production, we saw that a large sigma TT, which indicates a large transverse polarized photon contribution, which might give us an access to transversity GPDs, and sigma TL showing a larger value than the GK model prediction hints that there's this longitudinal polarized photon contribution is still significant. So we might be able to access the chiral even GPDs in this kinematic still. And from the NPS development that I contributed, we decided from the background those calculations, we decided to use a lower PMT gain, and we will have the thinnest material, less material between the crystal as possible, while keeping them in a uniform array with carbon fiber frame. And we will use an optical bleaching to maintain the energy resolution of the calorimeter to its optimal states during the whole experiment. So from this whole C experiment, we will further constrain on the GPDs extraction by separating the sigma L and sigma T term. We also measured the radiation hardness of a new glass scintillator. Although the developments is in still early stage, they look promising. And hopefully, depending on its final energy resolution and price, etc., its coverage on the EIC calorimeter will be decided. So the whole A DVMP analysis will be published soon. And the detector is still under construction in the IJC lab, and it will be hopefully delivered by the early 2021. And we will test on site, and the experiment was expected in 2022. I'm not sure now these days. And I believe most of you know that EIC project has started, and there is R&D, and there will be R&D for the next few years, and hopefully starts construction in 2023. And hopefully again, the operation of the EIC will start in 2030. Thank you.
Okay, thanks a lot for your great talk. It's really nice. I already have a few questions myself, but let me first open the questions to someone else. I'm sure there are some questions.
Thanks for the talk, Hassan. I had a question about the target in the whole A. You said that this was a liquid target. What is it? I think you said it. What is it made of?
It's liquid hydrogen target.
Hydrogen. Oh, okay.
Sorry
yeah.
if I didn't convey it well.
Okay. And what size is it?
It's 15 centimeter and about 5 millimeter in radius. So it's a cylindrical liquid hydrogen target.
Okay. And
5 centimeter, yes.
Is there some challenges associated to having a liquid target? Because I guess there's a container to it, and so you have to go through the container too.
Yes. So since due to the beam intensity, we actually circulate the liquid hydrogen from the outside reservoir, and we keep them in contact with liquid helium. So that provides lower temperature for the liquid hydrogen.
Okay, I see. And does the beam interaction with the container of the targets, you know, I don't know if it's in the tube or whatever, do you have some contamination due to that?
We don't have the contamination, but we clearly see, so the liquid hydrogen target is in this thin aluminum container, and we can actually see this aluminum container effect on the edge of the target by looking through this high resolution spectrometer. So we just cut these events at the side, at the edge of the target, and we use only the inner part of the liquid hydrogen target.
Okay. Okay, thanks.
Yeah, maybe a little bit related to this. It's a bit of a beginner question because I'm always from the LHC side and I don't know much about fixed targets, but can you say a little bit more about what is, for example, the chance that if you shoot an electron beam at a target, that this proton that you also want to identify using this mission mass technique you show here, what is the chance that such a proton then, for example, flies out into your detector, or is there also a high probability it's just, let's say, still stuck in the target or so?
It flies out.
Like
They fly
always?
out, but yes.
Yeah, yeah.
They always fly out, and there's always this resonance particles also creating, but with the calorimeter, by giving a certain cuts, we just remove those events. And one of the very first DVCS, one of the very first experiments in Jefferson Lab for this kind of exclusive DVMP and DVCS, we also had this proton detector made of plastic scintillator. So we just have this exclusive events, not using this missing mass technique. But you know, proton is hard to detect with thin plastic scintillator, and the efficiency was not good. And it turned out the electromagnetic calorimeter has decent energy resolution. So at the end, we decided not to use the proton detection.
And what do you then actually fill in for this formula that you have here? So you want to calculate M. I suppose E is just your incoming beam energy, and E accent is the electron that you just measure, right? That's
yes. So electron beam energy we know from the beam, and this proton for momentum, which is just the rest mass of the proton. And E prime
so that's an assumption. Yeah, I was wondering, like, if you don't measure your proton, what did you fill in for
yes.
P? Yeah. Okay.
It's around, yes.
Yeah. So you still assume that it's really not relativistic. So
it's few Kelvin. So.
Oh, okay. Yeah. Okay. Then
yes.
I understand how to calculate all of this. Yes. Okay. Thank you. Anyone else with a question?
I have another beginner question, Hosan. On slide 23, where you were showing your cross sections.
Yes.
What does it mean to have a negative cross section?
Oh, yes. It's, we call it cross section, but it's actually the interference term. So positive or negative doesn't really mean that much, because the sum of this cross section is actually related to the number of particles that we detect. So these are just the interference. So I cannot say any meaning of this negative cross section. It's just negative interference term.
So how do you get it? I guess this was a measurement, so how do you even get it to be negative? Is that just because there's the cosine in there somehow, or?
Yeah, so what we do is maybe I should have put it in the backup. So we will see this modulation of the number of events along phi distribution, right? And then we fit this cosine and cosine 2 phi. By this fitting, these terms, this sigma TL, these terms that we want to extract can have negative or positive depending on the fitting.
I see.
That's
I got you. So you measure the variable on the right, this d sigma pi 0, and then you fit, then it's the magnitudes of the cos phi and the cos 2 phi that you're showing.
That's
okay.
basic.
I got it. Great. Thank you.
I would also be interested if you can maybe say a little bit more about the clusterizer that you use, because I'm also very much using a calorimeter myself, actually also for pi zeros. So you mentioned you do this, so you have a seed threshold that is a 2x2, but do you have then more of an elaborate algorithm that aggregates no matter how large, and do you try to split clusters with some unfolding, or if showers tend to overlap or so, or can you say a bit more about that?
Overlap, for the overlap, this algorithm cannot do. This algorithm is more optimized for how to say, giving address to the energy to the photon, giving energy to the how do you say, assign each blocks to each photon. So what did I say? Sorry. It's not good for overlapping particles within the one crystal. It's a well-known algorithm called, I forgot the name. So how we do is we actually firstly design the calorimeter that always the particles that we want to detect will at least be separated by one crystal. So that way we ensure there will be no particles hitting one crystal or crystal right next to it. And then what we do is we find this local maxima, which will be where the particles actually hit. And we look for the neighbors, and then we assign these neighbors to this maxima.
Yeah. Yeah, because in this, I see it now. So what you have here on the top left, it's like it's one event, right? That triggers 4 different 2x2 patches.
Yes. So this is not an actual algorithm. Yes. This is not an actual algorithm. This is how we give a threshold to the calorimeter, a local threshold of 2x2. And after this blue clusters, we will have a bunch of these blue clusters in the calorimeter, all over the calorimeter, right? Using that, we then assign which photon belongs to which blocks, which crystal belongs to which photon.
Okay.
So yes,
but the blue block would be considered, let's say, the photon, for example, like the sum of the amplitudes there would be a photon.
Yes. Yes. So this is energy in GeV unit. So we expect photon energy from 1 to, for pi 0 case, 1 to 4 or 5 GeV. Of course, if the decay is asymmetric in the left frame, one photon will have all of the energy, but we expect that kind of range, and we kind of expect what the threshold should be. So for this case, this will be photon. This can be also other particles. It's just a background particle, but we have this a trigger window, and we also reconstruct the mass of the pi 0 later. So that's how we remove the backgrounds.
Yeah, thanks. That's clear. And let's see if someone else still has a question.
So if
Sorry,
no one has, oh, go ahead, Hannah.
I'm just still staring at this, and maybe I'm a little bit slower to recover from your explanation, but can you explain again the difference between what a hardware threshold and a clustering threshold means?
Yes.
I don't really understand why these would be different.
Sorry, yes. I didn't explain at all, so it should be confused. Hardware threshold is the threshold that is just given by the mechanical or electrical design of each of the PMT and crystal. So when we actually build a calorimeter, each PMT has actually different properties, also depending on the crystal. So we have to give it has certain threshold to the electronics where the particles hit below this certain energy, we won't detect anything. And above certain energy, we will start to detect energy. That's the hardware threshold. And from that, we detect something like shown here on the left. And those something can be backgrounds or noise from many other things. So we have to, we give certain threshold above those hardware threshold to ensure that we are seeing something out of nothing.
Okay, so the lowest that the clustering threshold could be, which is what it is in the red box, is like 1.1 GeV then.
Yes, if the hardware threshold is, for example, 1.1, we don't need to go below lower than 1.1, yes.
Okay, so it can be, the clustering threshold in this case was set to 1.35, but it really could be anything above 1.1.
Yes,
in
and
theory. Okay.
yes, in theory, yes, but.
Okay, thanks, that's helpful.
So I was saying if no one else has a question about your talk, I was curious to know, you said you are doing something completely different now. What are you working on?
It might have been really good if I put some slides for that. Sorry.
You don't have to.
I joined the RN's relativistic nuclear collision group in Berkeley Lab. Before that, I did electron-proton scattering, where we use alpha coupling constant around here. But now beam energy scan is now going on the other side, on the here. Well, that's not a good analogy. So now I'm doing beam energy scan, and also currently and focused on detector construction for the S-Phoenix. It is an MVTX MAPS-based vertex tracker. It uses silicon MAPS sensor. So before that, I did electron-proton scattering and detector design with a crystal. Now I'm going to gold-gold collision and silicon detector construction. So to me, it's very different. Lots of learning curve.